This video is on reading solubility curves. So there's a limit to the amount of solute that can be dissolved in a particular solvent. Now, for simplicity's sake, in this class, we are going to be only dealing with water as our solvent because most of the solutions that we make are water-based solutions or aqueous solutions. So this limit is called a substance's solubility. It is determined experimentally and does change with temperature. Now, for most solids, as temperature increases, then the solubility or the maximum amount that can be dissolved does increase. And so over here we have a solubility curve for potassium nitrate. So temperature is usually on this axis, and solubility would be on our y-axis here. That solubility does have kind of strange units. It is grams per 100 grams of solvent. Now, since we're dealing with water, and water has a density of 1 gram per milliliter, 100 grams is the same as 100 milliliters of water. So 100 grams, 100 milliliters, it doesn't matter what we're talking about, which we're talking about here, because they are the same thing. So you want to be conscious of those units for solubility, because sometimes you can get questions where they're going to ask you what the solubility is in something other than 100 grams or 100 milliliters. But we'll get to that in just a minute. Now, this solubility curve right here has a lot of different substances. So it not only has that potassium nitrate that we were dealing with before, but it has lots of other substances as well. And you can see for the most part, most substances, as temperature increases, the solubility does increase as well, since most of these tend to be positive slopes. So, just in reading this particular graph, how many grams of potassium nitrate can be dissolved in 100 milliliters of water at 50 degrees C? So you want to start, if they give you a temperature, with the temperature. So at 50 degrees C, we're going to start here, and then we're going to go up this grid mark until we hit the line for potassium nitrate. Then where the 50 crosses that line, we can go over to the other axis, and we can see that 80 grams of potassium nitrate can dissolve in 100 grams of water, or in 100 milliliters of water. Well, let's look at a different substance. Same temperature, 50 degrees C. Now we want to look at sodium nitrate. So as we go up 50 degrees C, we have to go to where the line crosses sodium nitrate, and then we're going to go over, and it's somewhere here between 110 and 120, so maybe like, it looks a little less than halfway, so maybe 114 grams of sodium nitrate can dissolve in 100 milliliters of water at 50 degrees C. So that's really how these graphs are read. You just have to make sure you go to the correct line and pay attention to those units there on solubility. All right, so solutions, we can describe them as saturated, unsaturated, or supersaturated. So a saturated solution means that no more solute can dissolve. We've hit its maximum limit. And if you think about, you've heard the word saturated before. If I were to say this paper towel is thoroughly saturated, that means it's holding the maximum amount of water and it won't pick up anymore. So when we talk about a saturated solution, it's holding that maximum amount of solute for that solvent at that temperature. So that means a saturated solution, those are the points that are on the line. That means they're holding that maximum amount at that temperature and no more solute can be dissolved. If you put more in, it's not going to dissolve and will just sink to the bottom of the beaker or container. An unsaturated solution means that more solute can dissolve. So we maybe have We've added some solute to the water and we've stirred, it's gone into solution. If we add more and stir, it's going to go into solution as well. Those are unsaturated solutions, so it's below the line on the graph. A supersaturated solution is a situation where we've tricked the solution into holding more solute than it should at that temperature. And you have to go through this whole process. And if you don't go through this process, you're not going to get a supersaturated solution at all. But you have to have really clean equipment, and you would bring your solvent up to temperature, so a pretty high temperature, and you're going to make a saturated solution. So you'll put solute in until it can't hold anymore, and so it's just kind of sinking to the bottom, and then you filter that solution off, and then you let it sit undisturbed, so you can't make loud sounds or stomp around the house really loud when you're making a supersaturated solution. And let it cool on its own very, very, very slowly. If you do that, we can trick the solution into holding more than it should at that particular temperature. Now, supersaturated solutions tend to be pretty unstable, and if you were to hit this solution that is now a supersaturated solution hard, what's going to happen is the excess solute, the more than it should part, is just going to fall out of solution. Or sometimes it causes other things to happen. So what I have here is a little video on a supersaturated solution. This is of sodium acetate. And we've made the supersaturated solution, so it's cooled down and it's holding more than it should at a particular temperature. And what you're going to see in this video is we're going to take a tiny, tiny little crystal of sodium acetate of the solid, and we're going to drop it into this solution. When we do that, it disturbs this unstable mixture and causes it to undergo mass crystallization. This thing also gives off a lot of heat, and a lot of times this is called hot ice because it's solidified and looks like ice, but is actually quite warm if you were to put your hands on the outside of this. And here it is again. You can see those mass crystals happening now in slow motion. If you were to turn this upside down, it would just be a solid in the container. It stays in the bottom. It's pretty cool. You can also, supersaturated solutions are also used to make rock candy. So in making rock candy, you make a supersaturated solution of sugar and you cool it down. And then you would maybe use a popsicle stick or something, or a string, and you can drop it into the supersaturated solution and it causes sugar crystals to form on the string or on the popsicle stick. That's not what I want to do. Okay, so now let's look at this in terms of the graph. I have 3 solutions, and we want to classify them as unsaturated, saturated, or supersaturated. All right. So solution A contains 100 grams of potassium nitrate in 100 milliliters of water at 40 degrees C. So we need to see what its solubility is at this temperature. So we're at 40 degrees C. We're going to go up and see the maximum amount that it could possibly hold. And at this temperature, the maximum amount it could possibly hold is maybe right around 70 grams in 100 grams of water. But we can see here that in solution A, I actually added 100 grams to 100 milliliters of water, or 100 grams of water. So the point is well above the maximum amount. So that means that this is a supersaturated solution that I have in solution A. Now for solution B, it contains 100 grams of potassium nitrate and 100 milliliters of water, but this time it's at 80 degrees C. So I go to 80 degrees C to see what its maximum amount is, and then over, and that's about 170 grams that can dissolve. That's its maximum amount, but I've put in 100 grams. So that's going to put this point well below the line. Since it is below the maximum amount, I can actually dissolve more at this temperature. And that means this solution is unsaturated. Now, if we look at solution C, it contains 250 grams of potassium nitrate and 100 milliliters of water at 100 degrees C. So I'll go to 100 degrees C and see what its maximum amount is, hit the line, go over, and that's at 250. So the solution at 100 degrees C can hold 250 grams of the solute. That's exactly how much I put in there. So this point is right on the line, and that means that solution C is a saturated solution. Okay, another type of question that you might run into in reading solubility curves. So this involves not making a supersaturated solution. So we're not going to go through the process of tricking this at all. We have a saturated solution of this substance in 100 grams of water or 100 milliliters of water at 60 degrees C. Then we're going to cool it down to 20 degrees C. And the question is, how many grams of solute will precipitate out of solution? So at 60 degrees C, you can just see from the graph, at 60 degrees C, this solvent can hold a lot more of the solute than it can at 20 degrees C. So the way to answer this type of question is to find the solubility or that maximum amount at each of these temperatures. So at 60 degrees C, we read that maximum amount. And maybe that's right at, let's see where my points are. Okay, 20 and 60. At 60 degrees C, maybe we're here at 110. That's how much a saturated solution would hold. And in the problem, they tell me we have a saturated solution. So I start off with 110 grams dissolved in this 100 grams of water or 100 milliliters of water. And then I cool it down to 20 degrees C. At 20 degrees C, all the solvent can hold is right around 40 grams. So what I need to do in order to figure out how much is going to precipitate out is, well, at 20 degrees C, it can only hold 40. At 60, it was holding 110. So the excess is going to precipitate out. So I take 110 and then I subtract 40 because only 40 grams can be held at 20 degrees C. And so that's a difference of 70 grams of that potassium nitrate that the solution or the solvent can't hold anymore. And so that 70 grams will precipitate out and be at the bottom of your beaker or flask or container, whatever it happens to be. So to answer a problem like this, when they ask you how much will precipitate out, you're going to find the solubility at each of those temperatures, and you just subtract, and the excess will precipitate out. Okay, so we just worked on this problem right here. Let's look at this problem right here. So it says how many grams of sodium nitrate will need to be dissolved in 200 grams of water to form a saturated solution at 40 degrees C. So with this one, at 40 degrees C, let's see what the solubility is. At 40 degrees C, the solubility of sodium nitrate is maybe around 105 grams. And that's how much will dissolve in 100 grams or 100 milliliters of water. But I don't have 100 grams of water. I have 200 grams of water. So since 105 grams will dissolve in 100 grams of water, that means double will dissolve in 200 grams of water. So that would be 210. So to answer a question like this, you have to be conscious of your units here on solubility. It's always in 100 grams of water. And if they change that, however they change this number, you have to change the number you read off the graph or the solubility. So again, at 40 degrees C, 105 grams will go into 100 grams of water. So 210 must be able to dissolve in 200 grams of water. Okay, so here I have a different solubility curve, and we have our solids, our solid lines, and our dashed lines are gases, and you have the key over here. And again, our axis here, our x-axis, is temperature. So as temperature increases, we can see the change in the solubility. Well, with this one, how is the solubility of gases affected by temperature? Because we've been talking about solids, and we could kind of see that with most solids, as temperature goes up, our solubility goes up. But if you look at the dotted lines, as temperature goes up, these are gases, and their solubility actually decreases. So as temperature goes up, the gas solubility actually goes down. Now, thinking about the kinetic molecular theory, this should make all kinds of sense because you get the particles as a gas moving pretty fast, and then you increase the temperature, they're going to move faster. And so they're not going to be as likely to stay in solution, and they'll just come up as bubbles and bubble out of your solution. And you know this from your experience with drinking soda. A warm soda is disgusting. And the reason it's disgusting is because it is flat. And the reason it is flat is because all the CO2 has left the solution. And that's because as temperature goes up, those gas particles are just going to leave the solution, leaving you with just the syrup left. Of course, as temperature increases, the solubility of most of these solids does increase. You'll notice here that sodium chloride is almost flat. So if you're making the solution of salt water, you don't really necessarily need warm water. It doesn't really increase your solubility at all, or not very much anyway. Okay, so that's the ins and outs of reading solubility curves.